Good morning, dear students. This is another video for both mechanical and civil engineering students. Simple bending theory. So, by using this simple bending theory, we are going to derive the equation for simple bending. So, what is simple bending or pure bending? Pure bending is the one there is no cross-sectional force across the cross-section. The net force is 0 and there is no resistance force between the layers of the beam. So these two are the important conditions. If the beam is obeying these two conditions, the bending is simple or pure bending. Before solving this derivation, I have to take some assumptions. One is material is homogeneous and isotropic. The material properties remains constant along the beam, and isotropic property means if you apply the force in this direction, the same force is applied in this direction. The same force is applied in this direction. The beam elongate in any direction, here, is same. That means the stresses in all directions is same if you apply the same force in all directions. That is called isotropic property of the material. So for our bending theory, the beam should be isotropic material, and the modulus of elasticity is constant throughout the beam. It should obey the Young's, that is Hooke's law. It should obey the Hooke's law. Then cross section must be plane before and after bending. The cross section before bending is like this, and it is having same shape like this. If it is changing its shape like this, it is non-planar. It cannot be obey the bending theory. Then beam is initially straight and all layers must be bent into circular arcs. So before bending, the beam layers are straight lines. After bending, the beam layers are circular arcs. Each circular arc is having certain curvature. The curvature is same along the depth, and it is having same center of curvature for this depths, and it is center of line of curvature. If you are extending the width, so it is B, and it is having another curvature behind this face. Okay, this is having same curvature, and neutral axis also having same curvature. The neutral axis cannot having change in length. So this is neutral axis radius from the center of curvature. This radius must be higher than all dimensions. This is another consideration. The dimension of center to curvature of neutral axis R is higher than width of the beam, length of the beam. Okay, this is the length of the beam, and partial depth of the beam and the depth of the beam. So all dimensions of the beam must be lesser than radius of curvature of the beam. Each layer is free to elongate and contract, that is, there is no resistance between the adjacent layers. These are the adjacent layers subjected to certain forces, and these are irregular due to resistance force between the layers of the molecules. So due to this, it is appearing in irregular manner. The stress distribution is not uniform. That is why it cannot obey the bending theory. When you take this one, the stress is uniform and there is no resistance forces between the layers. So that is why the stress resistance is not offered by the adjacent layers. Then another important assumption, that is neutral axis cannot contract and cannot elongate. All the layers must be either contract or expand during bending. After bending, the layers may contract here, may expand here. Okay, bottom layer will expand subjected to tensile stress, and top layers will contract subjected to compression stress. Neutral axis cannot elongate or contract. This neutral axis length remains same before and after bending. So this is the length of the neutral axis n here. After expansion it is also n. So n dash, same length. So what is the neutral axis? Neutral axis 1, which passes through the all centroids of the cross sections and which cannot subject it to either compression or tension. So this is the neutral axis. Watch this figure. This is the neutral axis passing through all centers of the cross sections. Okay, this is cross section 1, cross section 2. This is a continuous cross section. This is another continuous cross section. Take it as a continuous some beam, certain length. And now for our derivation, we are concentrating on elementary beam, element of beam. So take the element length is delta x. This is delta x length. Taking the points A, B, C, D. So this is AC layer. This is neutral layer NN. This is a EF layer. This is BD layer. So when you looking from here, front view, so AA will appear and CC online same. So A is A, C is C, N is N, B is B, E is F, E is E, F F. So like this will appear. You know that. This is the width, this is the depth. Now taking the differential element layer from depth y from the neutral axis. This is the depth y, this is dy. This is the differential layer. Okay. This differential layer is having certain depth from the neutral axis. Now we are considering such type of layers across the cross section and deriving the equation of bending. How you can solve this? Let us take this is the before, this is after bending. So before bending, beam is like this. So this is neutral axis. This is the layer or layer with thickness dy. This is depth y. This is total depth, capital D, small d. Okay. This is A. This is C. This is AC. This is BD. This is our consideration layer E, F. This is N. Assume this length delta x. So after bending about a curvature, it will deform like this. This is the neutral axis, changing to n dash, but there is no change of this length. This is A to C, A dash, C dash. Then B to D changes to B dash, D dash. Then this is the elementary strip, taking it as a line, thick line, point E, F, changing to E dash, F dash, EF, EF changing to E dash, F dash. Okay. This is the angle of curvature, theta. It is the radius of curvature from center of curvature is R, neutral axis length from center of curvature. Now this is additional length called Y. Okay. Now let us consider the strip length dx, delta x, after it is expanded into delta x dash. Okay. Now what is strain in the layer? Strain in layer means our layer, differential layer. That is E is equivalent to change in length by original length. Change in length divided by original length. What is change in length? This is initial and final difference. Final length is E dash F dash. Initial length is EF. Original length is EF. So what is change in length? E dash F dash minus EF divided by EF. Okay. This is the strain in the layer. How you can solve this EF? Okay. What is EF? Now take here from this figure. So what is this? A, C layer is equivalent to N layer, lengths of EF layer, that is also equivalent to BD layer is equivalent to delta X. Okay. Now take this NN is equivalent to EF is equivalent to delta X. Look at here. What is N dash cannot change. It cannot change. N dash length and N length are same. N dash is equivalent to N dash N dash. So according to our assumption number 7, the neutral axis cannot contract and cannot elongate. Okay. So length of the neutral axis is constant. Okay. So that's why N dash is equivalent to N. So what is this? This is the sector with angle theta and length of radius R. You know that E dash F dash E F is equivalent to N is equivalent to R theta, R into theta. So finally you can say this is EF is equivalent to R theta. Then come to this after elongation. What is E dash F dash? So E dash F dash is the new length. So take this radius of curvature is R plus Y. Same angle of curvature theta. We know that what is R, final R of this layer, that is R plus Y. into theta. So this is equations. These two are the equation A. This is equation B. Substitute A and B here. So what is this? This is r plus y theta minus r theta divided by r theta. This is equivalent to r theta plus y theta minus r theta divided by r theta. Okay, so you can get y by r theta, theta cancel. This is y by r is equivalent to E. This is the strain in the layer. This is the strain in the layer. Then what is the stress in the layer? So what is stress? By Young's law, also by Hooke's law, stress is directly proportional to the strain. So if you remove the proportionality, you will get Young's modulus constant into E. So substitute this. This is C equation. Substitute this C equation here. You will get E into y by r. It is the bending stress. This is the bending stress. Take it as D. Then extend this equation like this. Sigma B divided by y is equivalent to E by R. So this is equation 1. Then what is the force in the layer? What is the force that will withstand for the bending? That is called resistance force in the layer. This is the resistance force, dF. So you can take it as like this, dF. I have written here, this is the resistance force by the layer. This layer will resist this much of force, dF. So what is the dF? So force is equivalent to stress into area. This is the stress. This is the stress, bending stress, positive bending stress. This is negative bending stress. This bending stress over this layer of cross section is stress is equivalent to force divided by this cross section area. Now we want to calculate this dF. What is dF? dF is equivalent to, right here, resistance force in the layer. dF is equivalent to stress into area. What is stress? Sigma B. Area is dA. Okay. So this is dF. So this is equation E. This is equation E. Now, what is the resistance force? What is the resisting bending moment? What is the resisting bending moment? So to calculate this resisting bending moment, take this line CF or CD. Okay, take this CD line. So this is CD. Here, this is the neutral axis. This is the layer of thickness at a length of, at a depth of y. Here, this is F point. Now changing to F dash. Now this is C dash, this is D dash after bending. Now this is the force, this is the dF, differential force on this layer. Now to withstand this, due to this there is a bending moment. Due to this there is a bending moment, that is dM. So what is bending moment? This force into this area. Now this is O, this is say N dash, this is N dash. About this point it will rotate. This is the bending moment. So differential bending moment exhibited by the layer over the about this point N dash. Okay. Now what is the bending moment? That is called resistance bending moment or resistance moment. So actually this is the final total bending moment. This is the total bending moment across this element over this entire beam. This entire beam bending moment we can calculate by the forces that you know. So this bending moment is applying certain forces across the cross section. So when you are considering this element of layer here, that force on the layer is dF. Due to this force there is a small bending moment called dM. Small bending moment called dM. So it is positive. Similarly, if you take the point here, a depth height like this certain y2, here it will bend like this. Okay. Due to this force dF, this is certain distance. Okay. Now what is the resistance force, or we may take it as bending force, bending moment by the total bending on the layer, and this is the resistance bending. We can say it as resistance bending, opposite direction. So resistance bending in the layer which cannot allow to bend, the beam, that is dM is equivalent to this force into depth from the neutral axis. That is, force is dF, area length is, that is depth is y. Okay. Substitute dF. What is dF? Already told, resistance force. dF is from E, sigma b dA. Sigma b dA. That is sigma b dA into y from equation E. Then what is sigma b from equation D? What is sigma b? This is equation D, this is equation E. Substitute these two here. Sigma b is E by R. E by R into y dA. Okay, you can write it as dM is equivalent to E by R by square dA. Okay, this is equation F. So this is resistance bending moment, resistance movement or moment of resistance at any layer, we can take this equation. Then what is the total resistance of moment for entire section? So add all such layers, limiting from n dash to d dash. So what is here? 0. What is here? Total y, that is y. Y is varying up to here, that is d by 2. Up to here, it is d by 2. We don't know what is d, that's why we take it as variation. This is varying, that is called y. Now to get total resistance of movement, integrate both sides. Integrate both sides. Integrate equation F, that is dm e by r y square d. Applying the limits here, integration of dm, total dm is m. It is 0 to y. E by r is constant. Integral 0 to y square dA. Okay. You know, from the fundamentals of moment of inertia, area moment doubles gives the moment of inertia. That is integral y square dA is equivalent to moment of area moment of inertia. Substitute this here. So this is E by R into I is equivalent to M. Extend this equation like this. M by I is equivalent to E by R. So this is equation 2. Equating 1 and 2. Equations 1 and 2. What is equation 1? Equation 1 is this one. Sigma b by y is equivalent to E by R. So by using this equation, you can calculate the bending stress at anywhere along the cross section, along the depth. Equating this 1 with 2, we will get M by I is equivalent to E by R is equivalent to sigma b by y. This is the bending equation. Simple bending equation. Take it as 3. So like this, you can derive the equation. In examination or anywhere, you need not draw this figure. For understanding, I have shown it clearly. But in examination, no need to draw this figure. You can start directly from here. Okay? You can solve it very easily. Everybody can understand easily. Okay? This is the derivation. Videos like చేయాలి, కొన్ని షేర్ చేయాలి, కొన్ని సబ్స్క్రైబ్ చేసుకోవాలి. సైలెంట్గా వినడం అనేది నాలెడ్జ్ ట్రాన్స్ఫర్కి పద్ధతి కాదు. సో ప్లీజ్ subscribe this channel, like this channel or share this channel. Thank you.